Hello and welcome to this video. My name is Abdur Rahman and the purpose of this video is to get you started with using NI Multisim before you take on Challenge 2. From your course Moodle page, you can download this document called Getting Started with Multisim. So it has all the step-by-step instructions to make you familiar with Multisim, and I'll be talking about the same things in this video as well. So in this tutorial, we will be making four kind of circuits. They will be a relatively simple circuits, and the purpose is just to make you a bit familiar and comfortable while making circuits in Multisim. So the first circuit is going to be a simple LED on-off circuit. In the second circuit, you'll be controlling the intensity or brightness of an LED using a pulse modulated signal. In the third one, you'll be controlling a high current load. We will see how it is done. And in the last one, we will be building a high pass RC filter. So, to get started, I would request you to start the NI Multisim software and open up the Multisim file that's called Multisim Bioreactor Test Bench. So in the challenge 2, you will be making a bioreactor, and we have prepared a test bench that you can use to build up your circuit there. So you can download the Multisim Bioreactor Test Bench file from your Moodle page, and it should look something like this. I have removed few of the blocks from these parts just for the purpose of this tutorial. Now I will jump to Multisim software to actually show you how we do things there. Okay, so this is the Multisim environment. If I want to place any component in this design area, I can use the top toolbar, and there you can find a tab called Place. If I click it once and then go to Component, this component database opens up. So here I can see that all the components are categorized into different groups. So we've got sources, basic, diodes, transistors. So like if you're looking for an AC or DC source, you should go to sources, then power sources, and then here you can select whatever you want. And once you click OK, you can place the component onto the project area. And for most of the basic components like resistors and capacitors, you can use the basic group, and here you can find resistor, capacitor, inductor, relay, switches, and components like this. Okay, so let's get started with making our first circuit, which is a simple LED on-off circuit. So let me first just populate the components onto the project area, and then we'll talk about it. So I will need a variable resistor, 1K will do it. I will need a switch. I will need an LED. a DC power source, and a ground. So perhaps these are all the components I need. Let me zoom in a bit. And now to make this circuit work, I just need to connect them. Let's suppose I need to change the value of this DC voltage source. I can double click on it, and if I change this value 12 to 5, so now it becomes a 5-volt battery. So to complete the circuit, I just connect the component terminals together. And to run the simulation, either I can go to simulate and then press this run here, or I can just click this play symbol here, or just press F5. So I've run the simulation and the LED is not lit up. Can you guess the reason? Yeah, of course, because the switch here is open. When I close the switch, the LED is lit. So if I click on it, it's again open. So I can toggle this switch and see how it switches on and off the LED. Another thing that I would like to highlight here is how you can use this variable resistor to control the LED. So if we close this switch and the circuit is complete, we can see the LED lit up. Now this is a variable resistor, which means that I can vary its value from 0 to 1 kilo ohm by using this slider. So 50% here corresponds to 500 ohms. If I increase its value, so you see, as I increased its value above 60%, the LED switches off. Well, this is because every LED has some rated current value, so it needs at least that amount of current to switch on. If I will reduce the resistance value, you can again see the LED lighting up. So on your left here, these are the simulated outputs of your Arduino board. So we can also power up this, control this LED circuit using one of the Arduino outputs. Let's suppose we use the output 1 here. So what I can do is that I can remove this supply. First I need to stop the simulation. Then I can remove this supply. And run the simulation now. So again, the circuit is working. Before we make our second circuit, let us see how a pulse width modulated signal looks like, and how to use a multisim oscilloscope, and how to export data from it. So on your test bench, you have this block here called PWM output. So what we can do is that we can select it and drag it onto the project area. And I need an oscilloscope to see how the output signal from this block looks like. So the fourth item from the top on this panel on the right is called an oscilloscope. I can click it and place one here. Well, to connect it, I can just wire it up like this. Well, if you want to make copy of a component, you can use Ctrl C and Ctrl V to copy and paste the same way you do in MS Word. And you can use Ctrl R to rotate a component. If I right click on it, the display of the oscilloscope opens up. Now let me run the simulation. Okay, so right now the duty cycle percentage is set to 85%. So let's see if we can reduce it. Let's take it to 10%. So you can see here that as I increase the duty cycle, the pulse width becomes larger. Well, to make our view clearer, we have some controls on the oscilloscope. So this is the horizontal scale setting, where I can select perhaps 5 millisecond per division to have a better view, or 2 millisecond per division. And this shows that I'm using channel A, and right now the vertical scale setting is 5 volt per division. So I'm reading 5 volts here. So if I make it 2 volt per division, so now my signal spans over 2.5 blocks. Perhaps now if I change the duty cycle, I can see the pulse width changing more clearer. Yeah, I can. Okay, now let's suppose I need to export this oscilloscope data to use it somewhere else in my project. So I've got this button here called Save. If I click it, it asks me to save the data. So I can save it in one of 3 file formats. I can save it as an oscilloscope data file, a text-based measurement file, or a binary measurement file. So let's suppose I save it as a oscilloscope data file. And I've already saved one file, and I can show you that. So this is how a typical oscilloscope data file looks like. So in the beginning here, it tells you the settings of your oscilloscope. Then here, it tells you what channels were connected. So it says that channel A was connected, but channel B was not connected. And then you have the actual data here. So these are the timestamps, and these are the voltage values. The second circuit is an LED dimmer circuit, which you can make by using this PWM output block connected to a 1 kilo ohm variable resistor and an LED. So let me run the simulation, and you can see the LED blinking. So we would like to note the DC current through this circuit, which I can measure using this current probe. So as I increase the duty cycle of the pulse width modulated signal, the DC current in the circuit should go up. So you can see an increase in the current after I increase the duty cycle. Well, to do current measurements and voltage measurements, you can use these current and voltage probes from here, or you can use this multimeter here. So if I place this multimeter here, I can use it to measure currents and voltages across the circuit. When I double click it, I get this display which allows me to select whether I need to measure current, voltage, resistance, or decibels. And this symbol here indicates an AC measurement, and this is a DC measurement. An important thing to note here is that we can only supply a limited amount of current using an Arduino output port. So the maximum value of current that an Arduino input-output port can supply is perhaps 40 milliampere. So if we have like a high current load, we need to provide an additional supply for it. So let's see how we can build a circuit in which we can use the Arduino to control a high current load. So this LED is not a very high current load, so perhaps we can bring some high current load from the component database onto our project area. So let me get a lamp. And I need a transistor, a snubber diode, and an additional voltage source. Let me change the value of this source to 12 volt rather than 5 volts. So this is my additional supply. This is the resistance in the circuit. Let me reduce it, make it a 30 ohm variable resistor. This is the high current load. So the ratings of this lamp are, so it's a 12 volt lamp and a 10 watt with a 10 watt power rating. So this is a MOSFET. And I think this completes the circuit. So what we have done here is that we are using a pulse modulated output from our Arduino board to control the gate current of a MOSFET. So this gate current in turn controls the drain current through here. So when we change the gate current, it in turn changes the drain current, and this current derives its power from this additional 12-volt source. So it doesn't take the power from this Arduino board here. And this diode here is connected as a snubber diode to avoid any back current flowing in the circuit. So let me run the circuit and see if it works. Okay, so we have the lamp blinking, which means it's working. And let us also see if we are able to control the drain current by changing the gate current. So let me put a current meter here, a current probe. So right now it's reading 156 milliampere. Let's increase the duty cycle. Okay, so increasing the duty cycle increases the drain current through the circuit. So our circuit works. So this is the way that we control a high current load using our Arduino board. So you use an additional separate power supply, and you need a transistor here. Now before we make our last circuit, which is a high pass RC filter, let us see how we can use the Multisim function generator to generate different kinds of waveforms. So I'll be deleting this circuit and placing this PWM block outside our project area. So from this right panel, the second device is a function generator. So I'll bring it onto the project area, and then I will need an oscilloscope. Okay. So to connect them, I will connect the positive terminal of the function generator to channel A, and I need a ground in the circuit. Let me get one from the component database. So that's how I have connected my function generator to this oscilloscope. If I double click this function generator, it gives me these settings. So what I can do here is I can generate a sinusoidal waveform, a triangular waveform, and a square waveform as well. So what the pulse width modulated output was doing, it was generating a square waveform where we could control the duty cycle. So we can do the same thing from here as well. Then it allows me to set the frequency, duty cycle, amplitude, and offset. So for the amplitude, if I click here, it asks me to select the appropriate units. So I've selected the peak voltage value here. So it's right now 10 volt peak. And from the oscilloscope, if you double click it, so you see the channel A vertical scale settings here, channel B vertical scale settings here, and the time base or the horizontal scale settings remain same for both of them. Let us suppose we generate a signal with a frequency of 100 Hertz, duty cycle 50%, the amplitude is 5 volt peak, 0 offset, and this is a sinusoidal waveform. Now let us see how it looks on the oscilloscope. When I run this simulation, so this is the display on oscilloscope. I can try to adjust it so that it looks clearer. Okay, so it says here that one block corresponds to 2 volts on the vertical axis. So the signal is spanning over 2.5, so it makes 5 volt peak and 10 volt peak to peak. So the voltage is correct. And another thing that a tool that I can use to make exact measurements over a waveform are these T1 and T2 cursors. So you see this yellow line here. So if I move it, it drags a point across the curve. And you can see the values here in the second row changing. So this tells me the time and this tells me the voltage. So at the peak I should expect something around 5 volt. Yeah, so it's around 4.969 volt here. And I have another cursor available that I can also use. So when I move this one, the numbers in the first row change. Okay, another interesting thing to note here is that it is possible for me to generate a complementary signal of this signal as well. So if I use the negative terminal here and connect it to channel B and connect the second terminal of the channel B to the same ground, well, to notice the difference here, I should change the segment color here. Let's change it to yellow. Okay, let's run it. So now I have two sinusoidal waveforms here, and they are complementary waveforms of each other. You must be noticing why one is smaller in amplitude than the other. Well, it is because the vertical scales for the two channels A and B are different here. So if I make them same, like this, so now you see that their amplitudes is also same. So they are completely same signals, just 180-degree out of phase from each other. Well, this brings us to our last circuit, which is we need to build a high-pass RC filter. So what is an RC filter? So an RC filter, of course, will consist of a resistance and a capacitor, and it will allow frequencies higher than a certain cutoff frequency to pass freely while blocking the frequencies below it. And we will use this function generator and this oscilloscope to monitor the performance of our filter. So let us make our filter. Let me start with placing a 82 picofarad capacitor. Then I need a resistor. Okay, let me place just any and I'll change its value in the design area. So I'm changing the value of this resistor to 230 kilo ohm. So here I have my basic high pass RC filter, and I'll be measuring the output across this resistor here. So what I would also like to do is monitor my input signal as well as the output signal on the oscilloscope. So I'm connecting channel A to the input and channel B to the output. So the output signal will appear as yellow colored on the oscilloscope. So I'm using a capacitor of value 82 picofarad and a resistor of value 230 kilo ohm. So if you know the theoretical equation for the cutoff frequency of a high pass filter, you should be able to work out what you will be expecting the cutoff frequency of this filter. So the exercise here is that you should keep on changing the frequency here, let's say starting from 1 kilo ohm up till 30 kilo ohm, and for each of the input signals you should make measurements of the output signal that you're measuring on channel 2 as well as the input signal. Okay, let's see how it is done. So when I run this simulation, let me pause it. So here I can see that this red curve is the input signal and this yellow one is the output signal. So with the frequency set to 1 kilo ohm, the output signal is much smaller as compared to the input signal. If I want to know the exact values at a point, so I can see that when the output signal, when the input signal peak is around 4.9 volt, the peak value of the peak value of the output signal is just around 1 volt. Okay, so like this I should note the output signal peak value and the input signal peak value at each of the frequencies, and at the end I should use these values to make a graph of the gain, which is the output voltage by input voltage versus frequency. And on the x-axis, preferably, we should have the frequency on a logarithmic scale, and on the y-axis, we should have the gain in decibels. Well, that pretty much concludes this tutorial video. I hope you have learned something from it, and I wish you all the best for attempting your challenge too.